In this video, we are going to learn about complex numbers in rectangular or Cartesian form. And the objectives are to introduce complex numbers, to define complex number j, and to define a complex number in rectangular or Cartesian form by its real and imaginary parts. All these numbers, you can see here, have one thing in common. They are all known as real numbers. This number in red, however, is not a real number. It is called a complex number. And it is this type of number that we're going to look into more detail in this video. First, I would like you to consider this quadratic equation, x squared plus 2x plus 2 equals 0. You should know that we can solve this equation by using this quadratic formula. But to use this formula, I need to identify a, b, and c from the quadratic equation. So let's do that. A is 1 because 1 is the coefficient of x squared. B is 2 because 2 is the coefficient of x term. And c is the constant term 2. Now that I know a, b, c, I can substitute in the values to find x. So I have minus 2 plus minus square root of 2 squared minus 4ac over 2a. Now let's simplify this a little bit. So inside the square root I have 4 minus 8. And 4 minus 8 gives me minus 4. At this point we're stuck here. We wouldn't know what to do with this. But let me simplify a little bit more. Let me write square root of negative 4 as negative 1 times 4. And recall this law of indices that says that I can split this square root up into separate square roots if what I have in the square root is a multiplication. So I'm going to do the same to what I have here. So negative 2 stays. And the square root is split up into square root negative 1 times square root 4. Okay, let's continue on the other side. So at this point, I have minus 2 plus minus square root of negative 1 times square root of 4, which is 2. Now I can now separate out this fraction into minus 2 over 2 plus minus square root negative 1 times 2 over 2. And the fractions will simplify to give me negative 1 plus minus square root of negative 1. At this point, I'd like to introduce you to j, where j is square root of negative 1. Hence, my x is negative 1 plus minus j, because square root of negative 1 can be written as j. Hence, x can be negative 1 plus j or negative 1 minus j. We conclude by saying that this quadratic equation has two complex roots, and they are negative 1 plus j, negative 1 minus j. This quadratic equation does not have any real roots because its roots are complex numbers. Now let's look at j a little bit more. Let's define j. When we deal with complex numbers, we shall henceforth denote square root negative 1 as j. What that means is, when you're dealing with complex numbers and if you see square root negative 1, replace it with j. Similarly, if you see j in a complex number, you know that it means it is square root negative 1. And since j is equal to square root negative 1, if I were to square both sides, I get j squared equal square root negative 1 within the square. And that means j squared is equal to negative 1, because the square root upon being squared will disappear. Therefore, from now onwards, we can actually define the square root of any negative real number in terms of j. And we shall do that in the next example. In this example, we are supposed to simplify this complex number by writing them in terms of j. Before this, you wouldn't know what to do with this, but now we do. Now we know how to simplify this in terms of j. I shall start by writing it as square root of -1 times 16. And then, applying a similar law of indices as you can see here, I can split up the square root into this. I can only do that because this is a multiplication. Remember, j is square root -1. So, square root -1 here becomes j. How about square root 16? It is just the number 4. So the final answer is j4. So j4 is the same as square root -16. Let's try another one. I have square root of -49 over 36. Let's do something similar as before. Write it as -1 times 49 over 36 inside the square root. And just like before, I'm going to use the same law of indices to split it up. Now, j is square root -1, so this becomes j. How about square root of 49 over 36? That will give me 7 over 6. Because when we square root 49, we get 7. And when we square root 36, we get 6. So the final answer is j 7 over 6. So j 7 over 6 is the same as square root of -49 over 36. Now we are to simplify j cubed. J cubed can be written as j squared times j power 1. Do you agree? Going by this law of indices, the power 2 can add to the power 1 to give you the power 3. So this is correct. What is j squared? J squared is -1, so let's replace with -1. How about j power 1? It remains as j. -1 times j gives me -j, and that is the simplest form. Let's try j power 6. J power 6 can be written as j squared with a cube on the outside. And I know that it is correct because according to this law of indices, the power 2 times the power 3 does give me 6. So this is correct. Once again, j squared is -1. So I'm going to replace my j squared here with -1 and the cube remains. So what is -1 to the power of 3? Isn't that just -1? And this is the simplest form. We usually denote a complex number by the letter z, where z can be written as x plus jy. And when z is written in this form, we say that it is in its rectangular or Cartesian form. Now let's look at x and y in more detail. X is called the real part of z. And the reason for calling it the real part of z is because it is not attached to any j. Another way to write real part of z in a shorter form is to write re bracket z. This also means real part of z. So similarly, y must be the imaginary part of z. Why is it called the imaginary part of z? It's because y is attached to a j. And in a shorter form, I can write it as I am z. So this also means imaginary part of z. Take note that both x and y are actually real number coefficients, such as 5, 2, -3. Now, in a case where x is 0 and y is not 0, let's see what happens to z. So z is x plus jy. So now x becomes 0 plus j, y remains because y is not 0. So what we end up having is z is jy. You notice that the complex number z has only one term, and that one term comes with a j. Hence we say that z is a pure imaginary number. So in this case, z is a pure imaginary number, and the real part of z is actually 0. It has no real part. Examples of pure imaginary number will be j6 or j10 or negative j2. In all these complex numbers, you realize that they only contain one term, and that one term has a j attached. Let's consider the next scenario. If x is not 0 but y is 0, what happens to z? Again, z is x plus jy. So x remains because it's not 0, plus j, y becomes 0. And what I have is then just x. Notice that z now has only one term, and that one term does not come with a j. Hence, we say in this case that z is a real number. You can see that its imaginary part is 0. It does not have any term with a j attached. Examples of real number will be 5 or 1 or negative 3.14. All these are real numbers. You don't see any j in them. To summarize, if z is a pure imaginary number, the real part must be 0. If z is real number, then the imaginary part must be 0. Let's try some examples here. I'm to find the real and imaginary parts of the following complex numbers. Let's start with a. A is z equals to 2 minus j4. I'm going to rewrite it a little bit to write it as 2 plus j times negative 4. This is the same as this. Looking at this, the real part must be 2. Why is the real part 2? Because 2 is the term of z that does not come with a j. Hence, it is the real part. The imaginary part of z must be negative 4, because it is the coefficient of the term that comes with a j. And that's my final answer. Let's look at b. b is given as z equals to j6. So what is the real part of z? Notice that z has only one term, and that one term contains a j. Hence, it has no real part. The real part is 0. What about the imaginary part? The imaginary part is 6, because 6 is the coefficient of the term that comes with a j. This is my final answer. Here is one more example. I'm given this complex number. Part A would like me to find a if z is a pure imaginary number. Recall from just now, we say that if z is a pure imaginary number, then its real part must be 0. So, what is the real part of z? The real part of z is a plus 3. It is the part of z that does not have j attached. So real part of z must be a plus 3. And since it's a pure imaginary number, the real part must be 0. So a plus 3 must be equal to 0. And a hence must be negative 3. Let's try part B. Find the value of b if z is a real number. Recall from just now also that if z is a real number, its imaginary part must be 0. So what is the imaginary part of z? The imaginary part of z must be 1 minus b, because it is the part that is attached with a j. So that's 1 minus b. And since z is a real number, imaginary part must be 0. So 1 minus b must be 0, and b hence must be 1.